In the Operator Assist project, ISYE is working on the reasoning engine component. The reasoning engine tries to assess a flexible conversational search. In a question-answering system, such as Amazon, we can ask, for example, to request a mobile phone. Can you find me a mobile phone? Then, Amazon chatbot starts to ask different questions about the size of the screen, color, and price as the additional contexts until realizing the exact product to propose it to you. This kind of interaction, we try to implement in the Operator Assist. What is new here? Well, it is not just pure language. We have additional information coming from sensors. The reasoning engine combines both data sources, the natural language dialogue as NLP, and the sensor triggers, to find as fast as possible the current issue question to give precise support to the operator. The efficiency of the reasoning engine is focused on the less number of interactions with the operator, and less confusion with the final support. The current engine is built on a hidden Markov model as the probabilistic framework, which fuses information coming from the assembly state estimator with the information from NLP as language dialogue. It aims to estimate what would be the most relevant issue questions at the given time during operation. It is a time-based system that takes into account the estimation of observed state, observed actions, and observed conversation to try to calculate with these estimations the probability for these issue questions at the given time. Also, it considers the historical data, meaning that if, for example, one specific question was asked 5 minutes ago, it is less likely to ask it again. These are the information the reasoning engine is trying to fuse. For the prove it case, 83 questions are stored in the assembly knowledge store. Each question has a dedicated answer. If the digital assistant does not use the assembly reasoning engine, all those issue questions will be presented on the user interface when the operator requests help by clicking on the frequent answer questions button. Then, the operator needs to navigate through all the issue questions looking for what he needs to finally getting the answer. Starting from a F.A.Q list, as the reference, the reasoning engine in this first case prepares a lookup table as a fixed QA table. When the sensor information coming from the assembly estimator is not present, the current context is not possible to be automatically determined. Then, in terms of efficiency, the conversational tree has only one level of depth. However, in terms of the visibility for operators, the conversational tree has 83 branches, one per question, which is not efficient. Here, the conversational tree aims at recommending the most relevant information for users based on input questions, external data using the natural language processing techniques. Applying human-computer interaction principles, in terms of presentation on the user interface, the list of questions are paged 7 by 7 items. Then, 7 items per page mean that the operator should click an average of 7.5 times to find the relevant answer. Assuming that all the issue questions have a uniform probability, for example, on the prove it case and without knowing the assembly state, all the issue questions should get a flat probability distribution. By coding this using the hidden Markov model, this is the chart over the probability of different states. Here, the reasoning engine does not know which is the current assembly state, but as you can see, even though having a uniform probability per question, you can appreciate that some issue questions have more probability than others. This is because some questions are active in several assembly steps and some are just dedicated to a specific step. So, already there is a ranking for issue questions. With the hidden Markov model, the state estimator triggers would be included to get the information about the current assembly state. Considering that the state coming from the state estimator is 100% correct, the reasoning engine knows that the operator is performing a specific assembly step, for example, step 5. In this example, the number of issue questions was reduced to 33. So, the average number of clicks required to navigate all the pages on the user interface reduces to 4. In step 6, after filtering the issue questions, the average of clicks is 5.5 because there are more issue questions dedicated to this step. Then, based on steps 5 to 8 from the prove it case, the computed average number of clicks reduces from 7.5 to 3.4, which represent a reduction on the confusion for the operator. However, the challenge is still on sorting the issue questions in the right order, giving the most relevant at top. The next step of the reasoning engine is to incorporate into the hidden Markov model not only the hardware signals, but the language signals, too. Also, the reasoning engine tries to see if it can handle flexible questions instead of the fixed list of questions available in the assembly knowledge store. For example, the question can be coded into the system as, where can I find part item profile 1440 by 40 with or without holes, which is a too long question. We are investigating if the reasoning engine can find the best issue question with a higher probability when having access to the external sensor's information, as well as to the historical data when, for example, the question that comes from the operator is, where is the profile? To do this, we are investigating how easily the NLP classifiers can do the mapping of the issue questions to the input question. We used Raza as an open-source NLP platform. In the manufacturing and assembly languages, there are a lot of specific words that can be found in the manufacturing domain like bench dog or angle bracket. We experimented with 100 sentences coming from 4 different domains of manufacturing, manuals, warnings, informative texts, and work instructions, considering the English language and 2 different pre-trained open libraries in Raza. The obtained accuracy is between 86 and 92%. Our challenge now is that first, we need to map the input questions to the issue question, and second, we need to generate the answer for that specific issue question considering the external information. At midterm, the reasoning engine is linked with all the system components. The reasoning engine is able to filter the issue questions out based on context information with the help of the probabilistic framework. Until now, the context is assumed to be perfect, but at the next step, we will consider imperfect contexts and try to see how many feedback loops would be needed to achieve precise support, while introducing these priority rankings using the probability framework. We will look at a not-fixed question-answer table with the help of NLP techniques. Thank you for your attention.